All right, guys, here we go. Crossing over the halfway mark here in chapter 7. So getting into 7.3, here's the 4 items on the agenda for this lesson. So still looking at some matrices. We're going to do a little more work with calculators on these. Let me give you guys the inverse process on solving them by hand. And then some new things that you won't have seen yet. We'll deal with some partial fraction work and fraction decomposition, and then eventually fitting a parabola into 3 points using our graphing calculator. So let me get into the first item on the list. So when it comes to solving a system of equations, and again, all this goes back to some things that you guys have done in the past. In Algebra 2, you guys had a whole chapter on solving system of equations, and you did eventually get into these guys where you had a system of 3. So now you have 3 variables, and that's why you have 3 equations. So for solving these, you would have done this in the past with an elimination or substitution process. And there is a way of doing these with matrices, but as you would find, it's quite the lengthy, tedious process to do this with matrices. What we're going to be looking at is when you are solving a system of 3, like this one is, this one is kind of at the point where we'd say, you know what, realistically, we would use technology in a case like this, right? With the larger systems like 3 or 4 or greater, we would want to take advantage of some technology work because doing them by hand just takes so much time. It's very inefficient. So we're going to look at how to do this on a graphing calculator. So here we go. We're going to use a matrix to solve this. 2 ways you can look at this. One is, again, right here, you can go into your matrix feature and do it from there. The other one is, and not all calculators have this, so I don't always sort of show this route, but under F3, there is a matrix menu in there that also allows you to do some of this on your home screen. So you can work from either one, but I'm going to kind of start with the route that more calculators would have access to, which is to go into my matrix feature like we've already looked at before. And so the first thing I need to do is create a matrix for my system of equations here. So I'm going to go over to Edit. Anytime you want to create a new matrix, you go into Edit. You simply type over the one that was already in there from the last time you did this. So what I'm going to do is, to create the matrix, we want the coefficients as well as the constants that you see on the right. We're putting all those into a matrix. So if I looked at all those terms, you can see there's 3 rows, and there's going to be 1, 2, 3, 4 columns that we put into this. So we're going to create a 3x4 matrix, and I'm just going to type in all the coefficients that you would see. So like there's obviously a 1 in front of that x, there's a -1 in front of the y, there's a 1 at the z, and 0 on the far right. So we're just typing in those values. And I'm just kind of going down the list. I'm going to do that for each of my 3 rows. So it looks like this. So once you've put in all those values, again, guys, once you've created this, it will stay there until you go back in and change it. So even if I hit quit and go back to my home screen, that matrix that you created in there is still in there under the title of matrix A. So I'm going to go back into matrix. And remember, all of your operations are under the middle column that says math. So for this one, we're going to go down to option B that says ref. Hit enter on that. And it just now needs us to name the matrix that we are solving. So I'm going to go back into matrix one more time. I'm going to choose matrix A and hit enter. And here are my answers. So here's how you interpret this. The answers are in the right column, 1, 2, 1. So you guys see the identity matrix right here. So we have an identity matrix. And what you're seeing is column 1 represents the x's, because that's where the x's were. Column 2 represents the y values, because obviously that's where they were. And then column 3 is going to be, of course, the z values. So if you notice within the identity matrix, look at where the 1s are placed. In the first column, the 1 is, or sorry, in the first row, the 1 placed in the x column, which means this is my solution for x. So x equals 1. Right here, the 1 is placed in the y column, which means this is my solution for y. And of course, here is the 1 placed in the z column. Here's my solution for z. And that's it. So we now have our solution for all 3 variables. X is 1, y is 2, and z is 1. And that's it. That's all we got to do on this. So very simple. I wanted to show you one kind of a special case. When you guys did systems of equations, there were 2 cases. One was the no solution case, and one was the infinitely many solution case. And the issue that you ran into and how you determine what your special case was is essentially as you solve this, whether it was elimination or substitution or whatever, graphing, when you solved it, you ran into that case where all of your variables canceled. And if all of your variables canceled, obviously you'd be left with only numbers. Well, if the statement that you were left with was true, such as 0 equals 0, or 5 equals 5, or 16 equals 16, if you were left with a true statement, then it was infinitely many solutions. A false statement would be one where all of your letters cancel, but you're left with a false statement, and so it's no solution. So if I had a false statement like 0 equals 5, right, that's obviously a false statement. So that's how I would recognize the no solution case. So here's how we're going to see it within the matrices. So I'm going to go back in. So second matrix, I'm going to go over to edit to create this new matrix. It's still a 3 by 4, so let me type in the new numbers. So there's our new matrix. So let's go through the process of solving it like we did the last one. I'm going to go back into matrix. I'm going to go to math. I'm going to go to option B that says R ref. And then I'm going to go back in and choose matrix A. And here's what we got. So what do you notice about the difference on this one compared to the last one? Right? Obviously, I did not get the identity matrix that I need to get in order to identify what my solutions are, right? And so I have these sort of mixed results. There's nothing down here. So here's what we're going to look at. What we're looking at is this final row. And here I am left with 0 equaling 0, right? I am left with a true statement of 0 equaling 0. And so when we have those true statements, that's how we know it's an infinitely many solution case. So just one of our special cases that we can recognize. They kind of explain it all on this next page. So anyway, here was the matrix that we got. So they're essentially saying, look what you have left. If I put the x's and y's and z's back in, right? I have 1x plus no y's plus 1.5z equals -1, right? So they put the letters back in, and here's the equation that you're left with. You could do the same thing for the middle row. Here's the equation that you have left, right? I can't solve this. It's not solvable because you have 3 letters but 2 equations. And then in the final one, of course, here's the key, is that 0 equals 0. So we can tell by this that it is not solvable. And in the final statement, I'm left with something that's true, right? And so we know this is an infinitely many solution case. So there's a certain way they want you to write this answer. Instead of just saying infinitely many solutions like you would have done in the past, we're actually writing a solution set in terms of z. So instead of giving it values like x is this, y is this number, and z is this number, obviously we can't do that for a case like this. but we can still give it some type of an answer relevant to the numbers that we're showing. So what they want us to say is, let's just put it all in terms of z. So this guy is going to represent my x's, this represents my y's, and this represents my z's. So because z is just z, we're putting all of this in terms of z, right? And there's other ways you could write this. We're all putting all these in terms of z. So what they did was they said, well, let's identify an expression for x. So let's take this equation, let's get x by itself. So if I subtract this guy over to the other side so that it looks like this, so this now represents an expression for x in terms of z. So this expression is going in for x. We're going to do the same thing for y. If we get y by itself, by subtracting over the z, I get this expression right here. Right? And so what we're simply going to do is say, okay, we're going to let 4 minus z represent our y answer. So we're going to put that one in for y, and then z is just z. And that's it. So this is at least a way of writing the answer in terms of z, even though we can't narrow it down to just a single value. So let me show you what the no solution case looks like, just so you can make sure we interpret the difference. Let me go back into my matrix real quick, over to edit. It's always hard to say that without thinking of the movie The Matrix, but we're going back into the matrix. All right, so 1, 1, -1, 3, 2, -1, -8, -3, and then 3, 2, -5, 8. So here's this guy right here. Again, I'm going to go back under matrix. I'm going to go to math, go to ref. Oops. Sorry, we need to quit and get back out to the home page before I start doing all that. Go back into matrix. Let me try that one more time. Let's identify matrix A, because that's where we put it. All right. So for this one, again, you'll notice if I were to put the letters back in, I have x minus 3y equals 0. I have y plus 2z equals 0. Right? That's not solvable because I got 3 letters in 2 equations. But look at the final statement down here. There's no more letters. That's 0x, 0y, 0z. There's no more letters. I'm only left with numbers, and the numbers I'm left with make up a false statement. Right? This one says 0 equals 1, which is obviously a false statement. Therefore, we know it's no solution. Okay. So how do we solve a system by hand? Of course, you guys have done this before. You've learned multiple methods. You can graph it. You can use substitution, elimination. Those are the 3 main ones. We're going to learn how to do it with a matrix using an inverse process. All right, that's what we're going to see on here. Let me give you the main idea first and why this works. Let's just say you had an equation that looked like this. I'm just going to say, let's keep it simple. Let's say 6. Okay, and I just said solve that equation. Well, how would you solve it? Right? You would multiply both sides by the reciprocal, or the inverse, of 2/3. Right? So you would say, well, I'm going to multiply both sides by 3 over 2. And that's how I would get x by itself, right? Because what happens over here? Well, when you multiply those together, you get 1. And when that gets x by itself, so it just becomes like 1x, right? And then obviously when you apply those two together, you get your answer for x. The 2/3, the original one, we're going to call that matrix A. Our variable matrix, we call matrix X. And the solution on this side, we're going to call matrix B. All right, that's the 6. So what you're seeing in blue are the 3 things that were already there, right? And so those, we're going to name those with matrices. So it was matrix A times matrix X equals matrix B. All right, so those are the three matrices that we're looking at. So when we went through this process, how did we solve it? Well, we multiplied both sides of the equation by the inverse of matrix A. We get all colorful on you guys today. So I'm multiplying both sides by the inverse of A. As you may have noticed, there is a certain order to this, right? There's a reason I keep putting this to the left of B, like I did up here, right? If you were using normal numbers, it wouldn't matter if you put 3 over 2 here or here, you would still get the same answer. But with matrices, we've already know that that's not true, right? Order does matter when you're doing matrices, right? And so the way that you do this matters. It matters that you do the inverse first and matrix B second, right? So I am intentionally writing it in the order that I am. So what happens when we do this process, right? Essentially, I am left with a 1 over here, an identity matrix, and so it's essentially getting X by itself. And what do I have on the right? I have the inverse of A times B. So this is the process that we're going to be doing to solve for X. So we just need to figure out what is the inverse of A, multiply it times B, and that gives us our solution for X. So this takes us back to, how do we find an inverse? Here's the setup, okay, that we're going to be looking at. It's coming from this system of equations right here. So basic system of equations, of course, we could use elimination, substitution, all that other stuff, right? We could even use matrices and do it in the calculator like we did on the previous ones. But I want you guys to see how we can do this without the calculator using our inverse process. So what they start out with is they start out by saying, let's identify what these three matrices are, right? Or I should go back to the red ones and say, what is A, what is X, and what is B? Let's identify what those are. So A is going to be the 4 coefficients. We call it the coefficient matrix that you see on the left-hand side. So the 2, the -3, the +3, -5. That's matrix A. Those are the coefficients. Our variables, of course, are X and Y. And B represents the constants on the right side of the equation. So those are the 3 matrices that represent these 3 letters. And so what we have to do is we have to figure out what is the inverse of matrix A so that we can multiply it times matrix B. So they said, okay, here's the setup, right? This is A, this is X, this is B. Right, so this is the setup that they're giving us. The same thing that I was showing you right here in red. That's our setup. So all I have to do is figure out what is my inverse of A and multiply it times B. I am not going to go the same route that they did over here. They made this a little more complicated than it needed to be. I'm trying to shorten this process for you. Okay, so my goal is to lay out this. Let's figure out the inverse of A and multiply it times B. So let's do a little side work over here. How do we figure out the inverse of A? Maybe I'll do it up here so I don't cloud up the space too much. So we said, remember, it's 1 over the determinant. So if I did my downward diagonal minus my upward diagonal, so -10 minus -9. That's like saying -10 plus 9. Very easy. So this one is giving us, oops, I don't want to do that yet. Let's just say -1. So 1 over the determinant is -1. And remember, we multiply that by that sort of altered matrix where the 2 and the -5 trade places. The 3 and the -3 change signs. So if I distribute this -1, I have my inverse. And that's what's going to go right here. So we now know that my inverse is going to be 5, -3, 3, -2. So there's our inverse. Matrix B is the 9 and the 10. And X, we already know, is made up of an X and a Y. So now we've achieved this goal right here. We figured out the inverse of A. We're going to multiply it times B to get our solutions for X and Y. So remember how we multiply these guys? You do a row times a column. So again, this is a 2 by 2. I'll write it this way. This guy's a 2 by 1. Remember, we can do this because those guys match, and the result will be a 2 by 1 matrix. It'll look like this. So if I did that row times that column, that gives me the guy on top, which is my X. If I do the bottom row times this column, it gives me the value on bottom, which is our Y value. So 45 plus negative 30. On bottom, I have 27 plus negative 20, which is 7. Here we go. Sorry, I was thinking two values, but there's our solution matrix. So again, we know X is 15, we know Y is 7, that's it. So this is the way that you can use matrices, one of the ways that you can use matrices to solve a system of equations. That's our inverse process. If you need a practice shot at this, I'm going to do one more with you. If you feel like you don't need another one, you're welcome to skip ahead to the next example to save you some time if you need to, but I'll go through this super quick. So my matrix A is going to be the 4 coefficients. 4, negative 6, 3, negative 5. My matrix X, of course, is simply X and Y. Those are the two variables. And matrix B is going to be the constants that you see on the right, which are 1 and 5. So this is the initial setup given matrices. We are simply going to figure out or isolate the X by doing the inverse of A times B. So the only really side work that we have to do on this is figuring out the inverse of A. All right, that's kind of the main work that goes into these problems. Because we already know B is 1 and 5. That's right, but this is the process, the solving process. So inverse of A, let me do that up here. Keep it kind of out of the way. So my inverse for A, again, is taking 1 over the determinant. So 1 over downward minus the upward. So negative 20 minus negative 18. That's like saying negative 20 plus 18. In other words, negative 2. That gets multiplied by that altered matrix. Negative 5 and 4 trade places. Negative 3 becomes negative 3. Negative 6 becomes 6. Okay, so for this, now I can distribute the negative 1/2. I'm going to show you a trick on this. So I'm going to distribute that negative 1/2 to all of these. Well, here's the issue. If I did that, yes, it gives me the inverse, but here's the problem. I now have some fractions in there, and I now have to go through this multiplication process with fractions, which is certainly doable, but it's tougher. So what I like to do is I actually save my fraction till the end. So I'm actually going to put in, let me get rid of my equal sign for a minute. So I'm going to take this inverse. In fact, it's already written. Let me just do this to make life easier on myself. There's my inverse. I'm going to multiply it times b. So what I'm going to do on this is, instead of distributing this guy and then multiplying by 1/5, I'm going to multiply this by 1/5 first and then distribute this to my answer. And that way I don't have to deal with the fractions all the way through. So I'm going to do this row times that column, so -5 plus 30 and -3 plus 20. And now I'm going to bring in this -1/2. So I get -25 over 2 for my x and -17 over 2 for my y. And so that way I can kind of save the fraction till the end, and it's like way easier. So anyway, there's our solutions. Okay, some new stuff. Partial fraction decomposition. So you can see some explanation on this on 542. Essentially, here's what we're trying to do. Let me show you the image. Sorry, my computer's just working real slow right now. So I'm currently filming this on the Friday before Christmas break. So everything's just moving a little slow right now. So here's what it's going to look like. So the goal on this, I'm going to scroll up a little, is to take one fraction like this and break it apart into the two fractions from which it came. So what we've done in the past is we've had to take fractions like this, create common denominators, and then add them together to get this. This process is simply the opposite of that. You are starting with the single fraction, and you're being asked to break it apart into those two fractions from where it came. So that's the process that we're going to be going through here. So guys, you can read more about it on this page. Right? It does come back to matrices, as you're going to see here in just a minute. But let me walk you through the process and kind of explain every step of what we're doing here. So it starts out with, here's the original, and we're going to start by breaking it apart. So I broke this down into these 4 steps that I can explain that you saw from the book. And let's go through these guys. So our goal is to take this one fraction and break it apart into these 2 fractions. For the top, we're leaving them as simply a and b, because we don't know what those are yet. The bottom is being broken down into factors. So if we were to factor this, you can see this would be x minus 3, x plus 5. Sorry, x minus 5, x plus 3. So there's our 2, that's our breakdown. So this helps us identify what were the 2 original denominators that we must have started with. So one of these guys must have been the x minus 5, and one of these guys, the other guy, must have been the x plus 3. Right? That's like where this all started, right? Because at one point we had to bring these 2 together to create this common denominator. So this is the original look. What we've done with stuff like this in the past is, what if I clear out the fractions by multiplying both sides of this equation by the common denominator? Right? It's always been a way of clearing out fractions within an equation. As you figure out what's my common denominator, let's multiply it to both sides and clear out the denominators, clear out the fractions. So if I were to take this x minus 5, x plus 3, and multiply it times both sides of this, here's what that would look like. So essentially, I am multiplying this times both sides of the equation. I'm just distributing it to this, and then to this, and then to this. So if you look at the far left, look at what would happen here, right? all of this is equal, so it would cancel. And I'm left with simply 5x minus 1 on the left side. Go over to your middle term, I should say. We would see that the x minus 5s would cancel, and I would be left with just the a times x plus 3. Bring down that plus, and then right here my x plus 3s would cancel, and I'd be left with just the b and the x minus 5. Alright, so here's what I have now. My goal is to take this side, or sorry, I should say take this side and make it look like this side, right? And so that's what I was meaning by this statement right here. So I want to get the left side to model the format of the right side. I want them to look the same model as each other. So if I were to, say, distribute the A, so I'm going to bring those two terms together. So it's going to say AX plus BX. And then those two terms together, 3A minus 5B. So I'm just kind of reordering because on the left side I can now factor out X as a common factor. I'm going to get A plus BX. And then on this side I have my 3A minus 5B, and I'm just going to leave it like that. They don't have a common factor anyway. So there we go. So now this is now fitting this description, because notice this is something times x and then your constant. So I now have something times x, and then this represents my constant. So this is now in the form of this guy right here. All right, and so we're going to show this as a system of equations here, because now that I can see that these two are in the same form, I can see that my 5 is the A plus B, and I can see that the negative 1 is this statement right here. So 3A minus 5B is representing the negative 1. Well, now we have our system of equations, and now we're back to any good old method of solving a system of equations, which of course for this chapter we are doing it with matrices. Let me go through that really quick. So if we do that same process with what we did in the previous example, so I'm just simply figuring out what A and B represent. Okay, that's my goal. So solve for A, solve for B. So I'm going to get my coefficient matrix, which is 1, 1, 3, negative 5. My variables are the A and the B. And my constants are the 5, negative 1. So again, I want to do the inverse of this times this to figure out what A and B are. So if I take the inverse of this guy, I got 1 over the determinant, so negative 5 minus 3. Let's see, negative 5 minus 3, so negative 8. And then remember, we multiply that times this altered matrix where those guys trade places. These guys change signs. So this is my inverse, and I want to multiply the inverse times B. And if you watch that last practice problem that I did, remember what I like to do on this is I save my fraction for the end. So I could distribute it right now if I really wanted to, but then it's just a lot harder to deal with fractions and then multiplying it times another matrix. So what I like to do is take my inverse before I distribute that fraction, and I'm going to do this multiplication step first and then do this last. So if I did my, let's see, row times column, so negative 25 plus 1, so negative 24 and then negative 15 plus negative 1, so I get this. Now I'm going to divide them both by negative 8. I like to do that at the end. So negative 8 goes into both these evenly, so this will be real simple. So negative 24 divided by negative 8 and negative 16 divided by negative 8. And here we go. So keep in mind what all this represents. This is my value for A. This is my value for B. So now I can go back up to this and plug those in. So I can now replace my A with the 3, replace my B with a 2. So I'm trying to get all this on here for you so you can see it. Let me write it from here. So I'm going to write this as 3 over x minus 5 and 2 over x plus 3 to finish it off. And there's my answer. So pretty lengthy process on that one. You guys see kind of the initial 2 steps. The initial 2 steps are really the only new part of this process, because from there you're back to just identifying and solving that system of equations. I'm going to show you guys one last thing. And we'll end on this. And this one's going to go by real quick because we're pretty much using graphing calculator to do this process here. So here's what's going on. Is we have 3 points, that one, and that one, that are on a parabola. Okay, so we're told it's a parabola, and we're told that these are 3 points that are on it, and our goal is to figure out, so then what is A, B, and C, so that I can write the equation of that parabola. Right? So first thing we're going to do is simply create a system of 3 equations by plugging these points in for x and y. So here's my model. So in the first case, negative 1 is going to be x, 5 is going to be y. So if I put that negative 1 in for x squared, obviously that's just going to be 1. If I put this, again, this negative 1 in for this x, I get negative 1. And then c is just c. So there's my first equation. Now I'm going to take the second point and do the same thing. 2 is going in for x, negative 1 is going in for y. So if I put 2 in for that x, I get 4a. If I put 2 in for that x, I get 2b. C is just c. There's no x or y there. And then one last time, let's put 3 in for x and 13 for y. So if I put 3 in for that x, I get 9a. 3 in for that x, I get 3b plus c. So there's my system. I am now just solving that system of equations for A and B and C so that I can plug them into this model right here and get the equation. And we're just going to do this guy again. When you get into 3x3s and bigger, really want to use technology to do that stuff. So here's how we did this at the beginning of the lesson. If you go into Matrix, go to Edit. This is let me show this. This is simply a 3x4 matrix, and we're just going to type in all the numbers as if I were to drop the letters. So across the top row, we got 5, 1, -1, and 1. I'm just going to go on down the list here. And so there's all the numbers in front of the letters. Go back out to your home screen. Go back into Matrix. Go to Math. Go to RRef. Identify that this is matrix A. And here's my solutions over here on the right. Of course, if you wanted those as fractions, you could convert them to fractions. I'm just going to keep them as decimals for now. So we now know that A is, so we solve the system. I'll just write the answers here. How about that? So I can now see that my value for A is -0.2. B is 0.8. C is -1.2. And so now I can fit those back into this model, and I have my parabola. And so now, of course, if we were to graph that parabola, you would find that it does pass through those 3 points. And that's it. And so I just made a side note down here that you can do this for any curve. I just did it with a quadratic, but I mean, you could do it for a cubic or 4th degree, 5th degree, all that stuff. Of course, you would need more points for higher order problems, right? So if I needed 3 points in order to do a parabola, because I had to identify 3 different values. I needed an A, a B, and a C. If you were going to do this for something higher, like let's just say, for example, I wanted to do a cubic function, right? You know, like the S-shaped curves, these guys. So if I wanted a cubic function, which looks like this, right? So if I wanted a cubic function, well, now I would need 4 points, and I would need 4 equations in order to be able to do something like this, right? So the bigger the curve, the more information they would have to give you, and the bigger the system of equation would be that you would be solving. And then, of course, we would want to do that with matrices within our calculator and not by hand. So, but that's it for 7.3.